numbers would be numbers such as root 2, non-terminating, non-repeating, basically, right? Non-terminating, root 2, root 3, root 5, even 2 plus root 2 and all that, right? So these numbers are irrational, right? Now, there is one more concept which we are trying to prove here, is rather trying to understand. So there is a concept here. So say you have a prime number, say 2, okay, and you have another number. This is a prime number which you have, and you have a number which is say 4. Okay, not 4. Let's take some other number, say 6. Okay. Now I'm looking at this number 6, and then I'm trying to square this number. So square this number as well. Square this number. When I square this number, I will get 36, right? Now if I divide the 36 by 2, what I get here is that 18. So 36, I'm able to divide this square of this number by 36, and also if I try to see if I divide 6 by 2, I will also be able to divide by 2. So I'll get 3 here. So let's take another prime number 3, and let's look at the same thing. So I try to divide 36 by 3, and I get say 12, and then when I try to divide 6 by 3, I get 2. Okay. Now let's another prime number 5, and then when I try to divide 36 by 5, it is not divisible. I will get a remainder 1, and then I try to divide 6 by 5. I'll also not be able to divide. Then I'll get a remainder 1. Okay. So the concept here is that if there is a prime number p, there is a prime number p, and there is a number a. Okay. If this is a prime number, this is any number. This is a prime number, and this is any number. So the concept here says that if p is able to divide a square, then p should be able to divide. Okay. So if it is able to divide a square, then it should be able to divide a as well. So in other words, if p is a factor of a square, then p is a factor of a as well. That's the reason, when you remember, when I was trying to tell you that 101, and I'm trying to see whether 101 to what all numbers will be able to divide. So I used to tell you that let's take a square root of this number and then see what all numbers I'll be able to divide. So if I'm able to divide a square root of this, then I'll be able to divide this also. Okay. So so wait, however big this number is. This concept is very important, because this is what we are going to use to prove certain things now. So if p is able to divide a square, then p should be able to divide a as well. Divide a as well. And make this proof. Okay, it's okay. So now let's say I have a number a. Okay. So I can represent this a as my product of prime number side. This is what we did. So any composite number can be represented as product of prime numbers. So now if I do a square of this, what will happen here is that this p1 into p2 into p3 into pn can be all squared. So if this is how it is written, for example, I just want to write something so that it is easily understandable. But here is the proof given. So now your number is say, for example, your number is say 6, right? As I was taking. So this 6 number could be represented as 2 into 3. When I did 6 is 36, then I did this 2 into 3 square, right? Then this became 2 square into 3 square, right? So now, can I say that 2 and 3 are also a factor here? So basically, can I not write this as 2 into 3 into 2 into 3? Can I write it like this also? Can I now say here that now 2 is a factor of 36? Right? Similar thing I'm going to say over here. So what I'm going to say here is that, so this implies, as I got this, this implies that P1, P2, P3 and Pn are all factors of, originally I know that P1, P2 and P3 are, Pn are all factors of A. Right? So this is what is the proof here. Alright. P1, P2, P3 could be anything. I just take something randomly. Now what they are asking you to prove that root 2 is an irrational number. So we are supposed to prove this. Okay. So what we use here is that we use something called proof by contradiction. So now in this case, when I'm saying that I have to prove that root 2 is an irrational number, what do I write here is that root 2 is a rational number. Yeah. So we will say that let's assume that root 2 is a rational number. Okay. If root 2 is a rational number, then I can represent it as so where A and B are integers and B is not equal to. Yeah, I mean you can term as, and also okay, that is also true. A and B are co-primes also.
Yes.
That extent, I mean, actually, I mean, to that extent, let's talk about this because we came to this part. So, for example, if you have a number like this 4 by 6, right? This 4 by 6 is a rational number. It's still a rational number, okay? But here, what has happened that 4 is having this 2 into 2, and then 6 is also having 2 into 3, okay? Now, when you remove this 2 and 2, then this becomes 2 by 3, and this is the basically standard form of writing this 4 by 6. But if I'm writing 4 by 6 as a rational number, I'm not wrong actually. Alright. So it need not be that always co-prime. But here my assumption is co-prime, that okay, remove all the common factors, and here we are at this level wherein both of them are co-prime. So this is also okay to write as I mean rational number. This is also okay. But in this case, 2 and 3 are co-prime. Okay. In the other case, 4 and 6 are not. Alright. So yeah, this is something to be understood. But yeah, what we have done over here that we have ensured that A and B are co-prime. So we have come to this level. Now, what we will do in the next step is that we will square it on the both sides. Square on the both sides. Actually, I want to somehow prove it that this is whatever assumption had been was wrong. Okay. So, for example, when I had to prove that it's not a girls' school purely, so I assumed it, and I took an example wherein there is a boy studying in there, and it was not found to be true. In this case, what I want to do is that I want to prove this, that okay, somehow this A and B, which is looking like co-prime, are not co-prime actually. Okay, this is what I want to prove here. So I mean, it doesn't matter actually. For example, so let's talk about this also. See, if I have a number like this, like 2 equals to say 4 by 2, something like this. Okay, I have something like this. Okay, so equals to 4 by 2. Okay, what happens here is that on the left side, what I get 4, and this becomes 16 upon 4, and this becomes 4. So squaring something does not change the equality. Okay, yeah. So this is something to be understood. So if it is there, it can also be there. For example, you can take any other example as well. For example, if I'm talking about a situation wherein, say I have got 10 over here, and then this I have got 2 into 5. Okay, so now there's a multiplication like this. If I square it, I get 100 over here. Okay, this I will get 2 into 5 square, right? So equality doesn't change if you square it on. Again, you will get 4 into 25, and you will get 100. So what I am doing here is that there is an equality which is true, but I know a method using which I can prove that this is not a rational number, and because of which only I am
Just
doing.
to prove.
Yeah. So square on both sides when I do, I get 2 upon a square b square, right? I cross multiply, I get a square is equals to 2 into b square. Okay. Now when I see this 2 into b square actually, so the square root of 2 is a number which is,
Yes.
you can write 2 to the power 1 by 2 also, and say you want to square it, root 2 square, then what will happen? This is 2 to the power 1 by 2 square, which is 2 to the power 1 by 2 into 2, and this will go as this is what. So basically what property I'm using is that a to the power m to the power n equals to a to the power m into n.
Yes.
So this is what it is. So any square root which is there, when you square it, the square root symbol goes and directly you can write. Okay.
Yes.
So this is what we did over here. Alright. Now look at this. Now I have got a number which is a square, and it is like having a factor of 2. Okay. So basically a square should be divisible by 2. Okay. Can I say that
Yes.
this implies that a square is divisible by 2?
Yes.
Just now we studied if the a is a prime, basically 2 is a prime number, and if it is able to divide a square, then a should be, a is also should.
Yes, sir.
So if a is divisible by 2, can I write a as 2m, something like this? Wherein,
Yes.
so, alright, so I thought I have to write it. So now I'm putting this back here. So this is 2m whole square equals to 2 into b square. Now here it will become 4m square equals to 2 into b square.
Yes, sir.
Then b square will become 2m square. So again, can I write this implies b square is divisible by 2? Then can I write b is divisible by 2?
Yes.
By 2, so this could be a number 2, 4, 6, something like this. So any number like this, can I write as 2 into 1, 2 into 2, 2 into 3?
Yeah,
Right?
we can.
B equals to 2b, right? So now look at a equals to 2m and b equals to 2. So what I'm seeing here is that a and b are having a common factor of 2.
Yes.
But when we started, we said that a and b are co-prime. So our assumption is wrong. Assumption is wrong. It means that this implies that 2 is an irrational. Now, since you proved it, you can use it as a result also. So, for example, if someone asks you to prove that 5 plus root 2 is an irrational number, for example, someone asks you to prove this. Okay. So again, what we will say that we will assume that let's assume, yeah, let's assume that 5 plus root 2
Is
is,
a rational number.
and the same thing we will write 5 plus root 2 equals to a by b. Okay. Now what I will do is I will write root 2 as a by b minus 5 on this side. Now this is my rational number. Okay. And I am subtracting some rational number. So my right hand side is RHS is rational. Right? My RHS is rational, right? RHS is right hand side. Basically this part, what I'm trying to tell you is that a by b minus 5 will be a rational number, isn't it? Why? Subtracting a rational number from a rational number, so I will get a rational number only, right? For example, 2 by 5 minus 3. For example, this is the number. Okay. So what I'll get here is that 5 as the LCM, and then I will get 2 minus 15, and what I'll get is minus 13 by 5, which is a rational number. For example, I subtract 6 by 5 minus 2 by 5, then what I get here is that 4 by 5, which is again a rational number, right?
Yes.
Subtracting a rational number from a rational number, I will get a rational number. Okay. So I'm saying that this part on equations right hand side, right, this is called right hand side of the equation. Right hand side of the equation. Right hand side is a rational number. But just now we proved that root 2 is irrational.
Yes.
Rational number cannot be equal to rational number. Okay. So what I'm writing here is that my LHS is irrational. My RHS is rational. So LHS is not equal to RHS.
Not.
Right? So it means that
Yes.
our assumption is wrong. Okay. Our assumption is wrong. So what I did here is I didn't even go to that extent to do anything, but I made use of this result itself, that this root 2 is an irrational number. I have already proved. So I just made use of that to prove that 5 plus root 2 is also an irrational number. So I will also do another one. We'll do together and see. So we'll have to prove root 3 is an irrational number. Okay. So what we will do here is that we will start from the basic irrational number. So we will do the same step. So we will say that root 3 is equal to a by b, and we will not write all those stuff, you know, that a and b are co-prime and b
Yes.
is not equal to 0. A and b are integers. Okay. And co-prime. Okay. Now again we will square it, then it will become 3 equals to a square b square. Okay. So now my a square will become 3 into b square. In this case, now a square is divisible by 3 because 3 is a factor here. So it's a square is divisible by 3.
Yes.
Clear? Because see, any number which is like this, like 3 into 1, 3 into 2, 3 into 3, 3 into 4. So all these numbers are divisible by 3, right? Because I can divide it by 3, I will get 1 here. I divide it by 3, I'll get 2 here. I divide it by 3, get 3 here. I'll divide it by 3, get 4. Any number which is of
Yes.
this form, 3, will be divisible by 3. Any number which is of this 2m form will be divisible by 2. Any number which is 4m form will be divisible by 4. Okay. So a square here is
Yes, sir.
divisible by 3. Okay. So this implies a is divisible by 3.
Yes. Sir.
So I can write a equals to 3m.
Yes.
So I will write 9m square equals to 3b square. So now b square is equals to 3m square. Similar thing I will have to write here again. That okay, this implies b square is divisible by 3. B is divisible by 3. So b can be written as 3b. Now I look at a equals to 3m and b equals to 3p. So there is a common factor of 3. So basically a and b are not co-prime. So our assumption is wrong, and that's the reason. Okay.
Yes. Sir.
Rational number and their decimal expansion. So what it is trying to tell you very in short, I will tell you. See, your rational number which is there, right? So rational number could be like this 0.3, which can be written as 3 by 10, right? This is the rational number. Or
Yes.
you can have a number 3.45 also, which is like you can write it as 345 divided by 100. Okay. Now you divide it. What can you do is by 5 when you divide it, what you get? 5, 6, and then 9. This will be 20, right? So this will be actually equal to 69 by 20 also. So this can be represented as this. Okay. Now 69 and this is divided by 2. I'm just writing 20 as a factor of 2 square into 5. All right. So here also this is 3 and this is divided by 2 into 5. Okay. Another number like 2375. Okay. Now this is 375. I'll write it as 375 divided by 1000.
Yes, sir.
Now let's divide it by 5 because this looks like this is divisible by 5. So this is 5, 7 ja. By 5. So this will be 15. This will be 0.8. Now this is 3 by 8. Okay. So now this can be written as 3 divided by 2. Okay.
Yes.
So this is all these decimals are terminating decimals, as you can see, right? Okay. So what this next thing is trying to tell you is that if your number can be represented as something like p by q, where q, your this denominator, can be represented as 2 to the power m into 5 to the power m format, then this p by q is a terminating decimal. So I will again to tell you, as you can see here in this example, this is the terminating decimal. What you got here is 2 to the power 3 in the denominator. This is also terminating decimal 0.345. What you got here in the denominator is multiplication of 2 to the power 2 into 5 to the power 1. Here also you got something like 2 into 5. So basically, whenever you have something in the denominator which is in the form of 2 to the power m into 5 to the power m, either 2 or 5 or both there, right? Then it means that it will be a terminating decimal. Is that what it is trying to tell you? This is what we did in the last class also, wherein we were trying to tell you that how many zeros will be there. So whenever you have a factor of 2 and 5, it means that there will be zeros actually. So in this case also, there were 2 zeros, but essentially what happened is they got cancelled out. Here too there were 3 zeros because in the beginning you know what is there. So you write, yeah, let's write 375 and you write 1000, right? This thing can be written as basically 375. Let's divide 375 by 5. What I want to do is 5 7 is 35, then this 5, then 5, then 15, and 5, 3. So what I can write this as 5 to the power cube into 3. What can I write this 1000 as? Again 1000, let's write 1000. This is 2, 500, then 2, 250, then 2, 125, then this is will be divisible by 5. This is 5, 25, then 5, and 5. So actually it is here 2 to the power 3 into, started with this 2 to the power m into 5 to the power n, but somehow this got cancelled. Okay.
5 and
Alright.
5.
Yeah. So now it is
Yes, sir.
come to this step, like 3 divided by 2 to the power 3. I'm going to tell you this. The next concept is this only, that just by looking at something, you can say that whether it's a terminating decimal or not by looking at the denominator. If it has got a power of 2 or power of 5 or both, then you can just simply by looking at it, you can say that it's going to be a terminating decimal. Is what it the concept says. So, for example, let's look at some of the example, and then you will be able to say that. For example, here, what I have got here is that 13 upon 3125. So what I can see here directly is that this is a factor of 5, right? So now since this is a factor of 5, this 3125, this decimal is going to be a terminating decimal. Now here
Because
too,
it is 5.
yeah, just because it's 5.
Okay.
Okay, either it has to be 2 or 5, but not anything else, right? 2 or 5. Okay, let's try to see that as well. So, for example, let's look at this 3125, right? What I want to do is 13 upon 3125. Now let's look at 3125. Okay, so 3125 is 5, 6 log 30, then 1 to 12, 10 to 5, then it will be 25, 625, right? This is going to be 13 divided by, again, I should have done this the other way around. So, 3125. So this is divided by, sorry, this is 625, right? Then again 5, 5 once, then 2, 5, then 5, 25, then 5, 5. So this is going to be 5 to the power 5, right? So there is no either 2 or 5, but there is nothing more. So if I try to divide it, what I will get is the terminating decimal. So let's see 3125 if I divide it by 30. So 13, I get a point, then 0, then it's still not divisible, then I put another 0, then I put another 0, it's still not divisible, then I put another 0, then I get this. Then now it's 1, then I'll try 4 times, right? This is 5, 0, 8. No? This is 1 to 9. Right? I get a 0, 0, then I get 1. Okay, this is gone. And just because of this, I will get another 0. Okay, now it's not still divisible, then I will get, right? And then we will try with this 3, then I will get this. Zero, then this is 2, right? So, right now this is gone, right? As you can see, this is a terminating decimal. So just because there was a 5 over here, right? Now this is 2 to the power 8 also, because 17 upon 8, as I said, so 17 upon 2 cube. So it should also be terminating because it's either 2 or 5 or 4, right? 2 is here, so 8 divided by 17, so this is 16. Then I get 1, right? Sorry, it's 2, right? 2, right? Then because of point, I'll get 0, 16, 4, then I will get 5, right? For example, wherein it would not be terminating, for example, this one, 343, 29 upon 343. Okay, I mean, it will take us time. 29 upon 343. So there is, it's not either divisible by 2 or 5, so I know that I'll have to just start dividing. So 29, this is 0. Now I get again another 0, 0. Then this is 9 times. I have written here, I have written 29 here. Okay, then I have put a point because it's not divisible. Then there's a 0, another 0. No, so it's not 8, actually 8 times. 9 is actually becoming more. So I got then 4 times.
One.
188, right?
Yes.
One, right? So it is, as you can see, this is just going on and on, right? So you can keep on doing, but it will not terminate, but it will start repeating after a while. But it will be a big number. So you can use a calculator and see. And since there is neither 2 nor 5, right? Because of this, this is not terminating. Okay. So this is the concept here. That's all the concept here. All right. There's nothing more here. Okay.